Hello everyone. In this video, we are going to talk about the momentum part of this chapter. So we have already covered A2, circular motion and Newton's laws as the first two parts of this video. So this is the third part of this chapter, and we are going to talk about momentum, conservation of momentum, impulse, how the conservation of momentum also take in consideration of collision problems, elastic, inelastic collisions, and two-dimensional collisions as well. So the first thing, we will start with the definition of momentum. So momentum is a product of mass times velocity of an object. Momentum is a vector quantity and it has SI units of Newton seconds or kg meter per second. Now, the momentum is merely, if we just talk about the magnitude, it is just mass times the speed of the object. But when we take in direction in consideration, a lot of things start changing because in physics, a more important quantity than the momentum is the change in momentum. So we mostly talk about change in momentum. The change in momentum is final momentum minus initial momentum. Again, the change in momentum itself is a vector quantity, so we have to be mindful of that. And the change in momentum always points in the direction of uh, the resultant of PF minus PI. So PF is like this, let's say, and PI is like this. Okay. Uh, So object is initial velocity is momentum is like this. So if I want to take the resultant of this, uh, I can take PF and then I can take minus PI, okay, and then I can take the resultant of that will give me change in momentum vector. So change in momentum is also a vector quantity. Change in momentum is also referred as J, where J is impulse. Okay, so impulse is change in momentum, and change in momentum can be caused because of two things. First, it can be change in velocity, and change in velocity, when we refer to change in velocity, it can be object speeding up, it can slowing down, or the direction of the object changes. All those situations are valid. But change in mass is also possible. So example of change in mass is like rocket propulsion. Okay, like when a rocket ejects the fuel, it's gained some speed. Okay, so in that sense, like losing the mass can also change the momentum of an object. So there are multiple examples of change in masses as well. We will go through few of those. Okay, but these are the two ways. Now, in most common, like 80% scenarios, you will get change in momentum by change in speed. But there are few problems that we will address where there is a change in mass has to be taken in consideration. Okay, so we can see that there are two equations. Momentum change can be mass being constant and velocity being changed, or momentum where the mass is changed and the velocity uh, of the object is constant. Okay, so now how the direction of momentum matters. Like in this scenario, we can see that a ball is being struck with a racket. The mass of the ball is given 100 grams, and the velocity in the initial before it hits, it's 20 meter per second, and after being hit is 30 meter per second. Most of the time, students just think that momentum is just change in velocity, and they subtract 30 minus 20. But here, the most important part is the negative 30 because it is changing in direction. So if you miss that negative sign, your answer will get completely wrong. So we have to be aware that uh, we have to take the directions of the velocities in consideration. Okay. Uh, One thing now we can talk about is the Newton's second law in terms of rate of change of momentum. So we know that Newton's second law is mass time acceleration, but that is just considering the mass being constant. Now, the actual Newton's second law suggests that. So I can, if I want to write Newton's second law, I will state that the net average force acting on object acting on an object is given by rate of change of momentum, or is equal to rate of change of momentum. Okay, so rate of change of momentum, we can see this equation to be forming as net force is equal to, so this is a net force. Okay, in most of the questions this formula is applicable whenever this resultant force they say, or you will find in questions they will always mention net average force. Okay, now net average force, whenever they talk about, so average words means we are only going to consider the final and initial momentums and the time taken between them. We are not going to consider what happens in between, so that's why it is an average. Okay, uh, if we talk in terms of calculus, this is like a derivative of this momentum. Okay, but since we are only going to deal with the non-calculus part of this, so average force is what most of the time you will see appearing in the question. Okay, so this can be time taken, or sometimes we can, in most of the question you will find this is a time of contact, an object spent. Okay, so then we can bifurcate this formula of change in momentum over time taken into two cases. So if the velocity changes, we know that the change in momentum, the velocity changes v minus u over t. And what is v minus u over t? This is the mass time acceleration. So we can see that the Newton's law that we have learned, Newton's second law, net force is equal to mass time acceleration, is the consequences of the equation that we have got, net, that the net force is change in momentum. Okay. Now the second thing that we need to see that if the mass is changing, then we have something that we call as delta m over delta t. That is a mass flow rate. This is one of the important quantities, and it has a unit of kg per second. Now, in the question, they will not always mention it is a flow rate, or they will not mention just mass changing. They will just say that this much mass is changing per second. So kg mass changing per second is the rate of change of mass. Okay, so this is very much important, rate of change of mass, if it is given, or if they are asking flow rate or something like that. So always be aware of this quantity, and in that case we can write the net force is equal to change in mass, or mass flow rate times velocity. Okay, so for example, 60 kg of water passes through a pipe in 10 meters. What is the mass flow rate? So we can write mass flow rate as 60 over 10 times 60, because we have to convert in seconds, and we will get 0.1 kg per second. Okay, so this is how we calculate mass flow rate, and we can see that there are two equations emerging out of this. Okay, then there's one important example. Imagine fan, some fan blade, okay, is rotating and pushing the air through it. Okay, this fan blade is rotating at a certain speed and pushing the air through it, so that it can propel a, let's say, a car or something, or a boat, let's say. So this is a propeller, and we want to calculate how much force this cart will gain, okay, if this is rotating at a certain speed. Now there are a few important quantities that we need to understand. What is flowing through this? The air particles, correct? Now air is a, like, we are not talking about single particle, so we are not going to talk about mass of air, but let's say we know density of air. So density of air is given, let's say this is rho, so which is a mass upon volume. correct? So how much air is being pushed, okay, per unit time? If I ask how much air is getting through the fan per second, if I ask this question, then what I get is the flow rate. Okay, and how we will see that? So mass is density times volume. Okay, density we know. Now volume, what we can take it as, like, imagine this is the fan blade, and the in time t, let's say in time delta t, this is the amount of air, this is the volume traced. Okay, this is the imaginary, like, volume, imaginary cylinder. Okay, so area, volume of a cylinder can be taken as the area, cross sectional area of the blades. So this is a cross sectional area of the blades, which can be taken pi r square, where r is the radius of the fan blade. Okay, into the delta L, which is the length in time t, the distance covered by the particles, air particles, in time t. Okay, so this is the volume. So we can write this density as area times dl. Okay, and in that case, what we can get it as, this is a mass. Now per second, if I talk about, then I am talking about change in mass per second. So I can just have change in length per second, and that will give me rho AB as my flow rate. Okay, so this is the derivation of this equation. You need to understand the part how I am getting those equation, not, and not just remember like this as a formula. Try to understand how we are deriving this, okay, because it is a useful skill in structured questions. Okay, and since we know that the net forces, whenever there is a change in momentum, with change in mass associated with it, so we can have change in mass times velocity, so we can get this type of equation. Okay, so this is applicable in a lot of cases. It is not just a fan blade equation, it like for the rocket as well. If we have the density of the fuel and in the cross sectional area, how much force is generated, we can calculate by this. Okay, so now one important thing that I would like to talk about is the graphs. There are two kinds of graph, where I have a momentum versus time graph. Okay, so if I have a momentum versus time graph, we need to remember that the gradient of this graph is equal to the net force. Okay, so from the graph we can get the net force, and the another type of a graph is force versus time. So if I have a net force versus time graph, the area under the curve, the area under the curve gives us change in momentum, or we can say impulse. Now there are a lot of questions related to net force and time diagram. Okay, so most of the time they will give you some kind of a mass, initial velocity being rest, and we want to calculate final velocity. So we can take the area of the graph first, we find the change in momentum, and then substitute the formula for change in momentum to get the velocity. Okay, so those kind of problems are also common, so this information is also needed. Okay, now before we talk about collisions, I will like to talk about an example where object falls, let's say an egg, and it has two surfaces. Okay, one is like a hard surface, and other is like a soft surface. Okay, and the question asks like the egg breaks on the hard surface, which is obvious. Okay, and doesn't break on soft surface. And they ask why. And we think like this is so obvious, like, but we have in this chapter we are going to talk about in terms of momentum, in terms of uh, impulse, in terms of time of contact. So what we need to understand here is the the answer for this question is very much very systematic, and it is not just egg and hard soft. It can be any person jumping from certain height on a snow or something, or it can be any object falling anywhere. So these kind of situation we have to always answer in terms of momentum. Okay, so how we will answer this terms of momentum? So if the objects have been falling on from the same height, okay, the velocity, they will have same velocity reaching the bottom just before hitting the ground. So, and once they hit the ground, the velocity will be zero. So, the change in momentum in both the scenario, change in momentum for both surfaces is same, because in both the scenario they are going to come to rest with the same velocity before hitting. Okay, then what's the difference? The time taken to change the momentum or to come to rest is higher for the soft surface. So this time is much more important part here, because time is taken more to slow down. If you have a soft surface, you will take a little bit more time than the hard surface. The hard surface, it will be very much immediate. Okay, and since the forces change in momentum over time, we can see that the time being more reduces the force. So thus, the force of impact is lesser in case of soft surface. Okay. So any kind of this question, we always rely on solving this in terms of change in momentum. Okay. And also one small thing that I can add is like, what is the force exerted by the ground on the object? So this is the force exerted by the ground. Now, if I want to calculate this force, remember that the change in momentum over time will give me the net force. And net force is not this force. Net force is like if there is a mg acting downwards, like a weight. So the force of the ground minus weight is net force. So change in momentum, if we know the velocities, we can find the change in momentum. In that case, if we know the weight, mass as well, we can calculate the weight, and then we add that to get the this force. Okay. Now we'll talk about the collisions. Now in elastic collisions, elastic collisions are very ideal. There are no energy losses, but in elastic collision there are mainly energy losses because of heat friction. Okay. Elastic collisions are with the small particles like atoms and molecules, and inelastic collisions are for the like body sticking together, explosion parts. Those are like the classic problems where we have, whenever you see a explosion or a body object sticking together, you can always know that it is inelastic collision. In inelastic collision, okay, momentum is conserved, and in inelastic collision, kinetic energy and kinetic energy is not conserved. Total energy is always conserved. Okay, that's the conservation of energy. But you can see that in elastic collision, kinetic energy is as also conserved. Now, what is this conserve? So we'll talk about conservation of energy first. Okay, sorry, we'll talk about conservation of momentum first. So conservation of momentum is very important principle in physics. So the conservation of momentum talks about two important things. First, if the net resultant force, net average force or net force, just force acting on an object or acting on a system of objects is zero. Okay, it can be net force, it can be some kind of external force, something the force that is outside the system. So net force acting on a system is zero. Then the total momentum of the system is conserved, or we can say it is constant. Okay, so basically the total initial momentum should be equal to total final momentum of the system. Now here the more important word is the system. Okay, because without defining what is your system, we can't conserve the momentum. So first we need to understand if there are two objects colliding, okay, in the space, there will be forces acting between them. Okay, but if we consider both the objects in my space as a system, then the momentum will be conserved. Okay, it doesn't matter what is the force acting between them, unless there is some external force present, the momentum will be conserved. Okay, if I drop a pen on a table, what will happen? There will be a collision. Now if I consider my system as pen and the table, in that case the momentum won't be conserved, because gravity is the external force coming from the earth, which is not in the part of my system. We need to understand that momentum is conserved, but we need to be aware, is there any external forces? Is there any forces that we are not considering in the given system? So this is where conservation of momentum plays important role. And this is the total momentum of the system. So it is not just individual objects. We have to take total. We have to add the momentums of the objects before and after. Okay, we will see an examples of this. But in elastic and inelastic collisions, we have to aware of two things. In elastic collisions, you will find that the kinetic energy being conserved. So total kinetic energy before collision, total kinetic energy after collision. So this is valid. First thing. The second thing is the relative speed. In an elastic collision, the relative speed of approach should be equal to relative speed of separation. Now, what is the speed of approach and speed of separation? So speed of approach is basically before collision, what is the relative speed? So you can take both the objects. So if both the objects are moving in same direction, so we have to subtract the velocity. So it can be v2 minus v1 or v1 minus v2. Okay. So this is or. So that is the relative speed. So this is the relative speed of approach. This is before the collision. Now after the collision, if the objects are in opposite direction, we have to add the velocities. Just remember that. Okay. This is just because the velocity being vector continuous. If we are considering vector, it will be uh, we are finding change in velocity. Relative velocity is the change in velocity. Final minus solution like that. Okay. So or we can take this as 2y. So v2 minus v1. Okay. Now when we have those velocity, relative velocity after collision and before collision, they have to be same in case of elastic collisions only. Remember this. Okay. So in case of elastic collision, these two conditions has to be satisfied. In inelastic collision, these conditions are not satisfied. So we have to be mindful of that. Okay. So law of conservation of momentum we already know. Okay. Now the two objects, you can see that I can take the momentum as m1 u1 plus m2 u2, and after collision it is m1 v1 plus m2 v2. Okay, so in that case what we will do is we will see that the momentum is added for both the object initially and finally, and then what we will do is we can find any quantity. For example, if there is any quantity that is unknown in this case, like u, v, v1, v2, or anything, using this equation, we can calculate this, and we can make sure those equations are helping us. Okay, so in this case, we will get that the change in momentum total into zero is final minus initial equal to. Okay, then in, whenever we see those kind of a problems, we need to know that we need to build a equation, and this is not necessary for only two objects. It can be for three objects as well, but we have to take the total momentum. Okay, then if there is a two-dimensional collisions, in case of two-dimensional collisions, we need to be aware that we have to conserve the momentum in both x direction and y direction separately. So initial momentum in x direction should be equal to final momentum in x direction. Similarly, initial momentum in y direction should be equal to final momentum in y direction. So if there is a velocities and angles, we need to break down in the components like y component and x component. Okay, and then we build two separate equations to satisfy this conservation. Okay, so we can see that in this particular example, m1 u1 and m2 u2 are the velocities both in horizontal direction, and after collision they are going to have v1 and v2, and they have making angle theta 1 and theta 2 with the horizontal. So in x direction, if I want to conserve, then m1 u1 is the initial momentum, m2 u2, so initial total momentum, this is the initial total momentum, and this has to be m1 v1 and m2 v2 x component. So these are x components specifically. Okay, so this is we get a one equation. Okay, similarly we can in y direction there is initial momentum is 0 before collision, there is no momentum in y direction, but after collision they have two components, so v1 sine theta 1 and v2 sine theta 2. The angles need not to be same. Okay, remember guys, and we get this another equation like equation 2. Now using both this equation we can calculate any missing quantity. Okay, and if it is elastic collision, we can apply the elastic collision formula as well. But change in momentum, if we see that the change in momentum vector is always pointing in the direction of, like, so for example, if I have a initial momentum and final momentum, then this is the direction of the change in momentum, like this. Okay, so change in momentum can be found for the individual object. Okay, but if I'm considering the, like, what is the total momentum of the system initially, so if the initial total momentum and final total momentum, like this is a net momentum, it has to be 0. Okay, so if I want to combine my initial momentum, so it can be x component square and y component square initial, and I can take the square root of that, like a vector quantity. Okay, and this will be equal to the final momentum magnitude wise as well. Okay, so we need to be aware of that. Okay, so in this momentum chapter, this is the only thing is there. Okay, I hope we have covered everything. Thank you so much.